Alright, welcome back to the SciMax channel. Today we're going to continue looking at the SDL-Light demo. And last time I did a design of experiment, I introduced the idea, but we did a very straightforward linear regression on the model as our model, and we got a good fit, we got good results, but we didn't do any kind of statistical analysis, no analysis of variance. We didn't really get into prediction errors or anything like that. And so today we're going to look into doing that and what is required beyond regular linear regression. We still do a regular linear regression, we just we'll leverage stats models today to get us some more quantitative understanding of the model. So I'm going to walk through the design of experiment again because we have to set it up again to run these experiments. So I used the Box-Banken design from the PyDOE3 package. This generates a matrix that we'll see later. I'm going to combine a bunch of steps here. The original design here comes as coded variables that are in the range of -1 to 1. And we have to convert those to actual measurements here. And so I convert the range to be within the range of 25 to 75 as the inputs for the R, the G, and the B. And then we convert those to integers because that's what we have to input to the device for the measurement. Here I set up the minimal code for getting data from the self-driving lab demo out in Salt Lake City. I also cache these results so we can get them again. I set up a measure function that returns approximately the R, the G, and the B channels. And then I randomize them here. And then we run our experiments and I tag these with July 5th, that's today. And this takes about a couple of minutes to run. And then what comes out of this is the results. So here is the table of results for the RGB outputs that we measured for each of the 15 experiments that we ran. All right, so that's all repetition of what we did before. And what I would have done before is generate polynomial features of the inputs and linear regress these outputs. For today, we're going to use stats models. So the first thing I do is create a data frame that we will use with stats models. And the data frame will have the inputs and the outputs. And to do that, I simply concatenate these results. And then I rename the columns so that we have column names because we will use our formulas in a minute that relate these inputs to these outputs like that. All right, so let's see, let's run this. And now let's talk about stats models. So there's a couple of ways to use stats models. I'm using the R style formulas here that say the R out column is equal, this is the R formula for equals, to R int plus B int plus G int plus these interaction terms. And then we have these quadratic terms. And then here I give it the data frame that we used, then we fit it, and then we'll get a summary. Now, one thing I'm not crazy about in stats models is you can only do one column at a time. And so here we have a model for the R out, and it's just a parabolic model in all of these. And when you run this, you get, here I'm fitting it, and then we get a summary. So let's have a look here at the summary. You see a very high R squared value. That's generally good news because it means that we have a good model. We have down here some coefficients, and let me make this a little bit smaller. We have the intercept. These are the features that we used. You see a large value for the R int. That makes sense. And then smaller values for the rest. But this p greater than t is the thing that we want to look at. We want to see values here smaller than 0.05. That means that those parameters are generally important. And we see only one parameter that is probably unimportant in this model, and that is one of these b times g terms. And if you remember the video from maybe yesterday, the dependence of the R channel on B and G was pretty minimal. So that's not super surprising. And if you wanted to, you could eliminate this feature from the model. You do see this note about strong multicollinearity. We sort of know there's collinearity in this data set because of the analysis we did yesterday. We're not going to worry about this particular thing. One thing that is nice, though, is now we can get a prediction, and the syntax is a little bit strange. We have to pass in a dictionary, but here I can make a prediction of what the model would output, and you get from the summary frame the mean value, the standard error, and confidence intervals of on various properties. So this gives you an idea of what range of values you might expect based on this fit, and that can help you determine things in the future. All right, so I did this also for the B channel. Similar story down here. Let's make this one a little bit smaller too. You see the biggest value here. This again means if I go from 50 to 51, I expect an increase of about 207. And here you can see almost all of the parameters are relevant, maybe except for this one. But again, this one is not super surprising. And we can kind of keep everything for generality. And then for the G output, again, another similar story. We see the G one being the largest, and most things other than the RB column aren't important, but the rest of the parameters are considered significant. Okay, so and then we can use we can also make a prediction here. So if I just want to predict a value, I can do that. Here I use the model to figure out what settings would give me the 10,000, 10,000, 10,000 setting. This again is a little bit clunky because we have to use this dictionary, I guess in this case I could have just made the dictionary once and then used it over instead of typing it out each time. But to find this, we want to find the R, G, and B values that minimize this sum squared term. Here I give it an initial guess. It finds a solution reasonably quick, and it's not super clear, looking at this exponential format. So down here I cast it as integers, and then we can leverage the prediction to see what kind of values we would expect to see from this. And so for red, we expect 9,900. That's quite close to what we saw before. And then these are the confidence intervals. And if I was to change this from 41 to 42, then you see it goes way above 10,000. And that again is from a video yesterday. You know that the space that's accessible is quite discretized. And so this one is 200 away, and this one is 100 away. So in fact, 41 is closer than 42 to this value. That's the same here. We can predict the G result. This one's actually quite close to 10,000, but that's certainly a coincidence. And the B result here gives 99.24. I think if I do, let's just do B plus 1 here, then you see this goes quite a bit higher, and that one's like over 100 away, and this one is less than 100 away. So in fact, we got to a good result that way in that dimension as well. Okay, so we're taking kind of step by step a more and more thorough analysis of the SDL-Light experiment. Here in this video, we focus on an analysis of variance or a statistical analysis of the models, and you can use these outputs up here to determine if your model is overfitting, or for example, we could keep adding terms to get I cubed and things like that. maybe for fun, let's see what happens if I do that. Let's just add an I cubed term. So if we do that, we get down to here, and that's interesting. This is still looking like it is fitting it a little bit better. There's hardly any error in that term, which seems kind of strange. And this coefficient is 0.0194. Let's look up here at the AIC and BIC. So 97 and 104. Those are information criteria. And they don't really change. Let me change this one to A. I guess, sorry, R. So rint, also a little bit surprised that that helps anything. Probably should have tried this before I did it on the fly. It's not obvious. You should. We can justify that. So we'll leave it here, I suppose. But these things like stats models give you all this information. The I forgot what A and B stand for. One is Bayesian information criteria, and the other one is something that starts with A, information criteria. You can use these, the trends in these as you add more and more terms to see if you should add or subtract. Like if I just did the simpler model, then AIC goes up, and as I add terms, it goes down. And what you want to do is, I believe you want to minimize that term. And you do that by kind of adding terms, but eventually the values might go back up. And as you look at these, these coefficients are kind of small. We could try to take them out. So this would give us different models that are different levels of quality, and it looks like we probably want to keep all of those in there. And that's probably true because we did see evidence of interactions between them where having, maybe it's not interactions. We saw evidence of one channel affecting the other channels. That's not quite the same as having these interaction terms. But down here it says these interaction terms are actually significant in some cases, but not all of them. So that's all for this one. The last thing I want to mention here is that this approach, this design of experiments, required us to do 15 experiments so that we could fit the model. Because we fit the model, this model has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters, including the intercept. You have to do at least 10 experiments to fit the 10 parameters. There's no way around it. And that's a feature of the model that we're using. And that model is fitted by linear regression and matrix algebra, and you just have to have the right number of dimensions. Or you run into fitting problems. I think next time I will show you that it's possible to get to this solution in fewer experiments that don't require at least the 10 experiments, but we can actually get there sometimes with even fewer experiments by using a different style of model that isn't limited this way. So that's all for today. This was just an introduction to using stats models to get a more thorough statistical analysis of the experimental results that we got. And next time, I think we'll look at a different kind of model that can still use the same data if you want, but doesn't have to, and can use less data and different data than this. All right, thanks for coming. See you next time.